16.3 Fundamental Theorem of Line Integral. We will continue the study of line integrals. Last time we defined the integration of vector field along a curve as that, and if we have a potential field, then this integral is particularly simple. Let's say curve is like this from point A to point B. Okay. Then this integral will be fx fy dot dx dy on curve, and that is fx dx plus fy dy. And if you remember, that's exactly the differential of this function. And along this curve means from this beginning point to the end point. So that's just the difference of the end point minus the beginning point. And this means if you know f, then the integration itself is just the function evaluated the two ends and then take the difference. And this is called the fundamental theorem of line integral. So this essentially says that this is the derivative of f. So the integral of the derivative will give you the original function. But if it's from one end to another end, then it's the difference between the two original functions. Okay, and how can this help? Well, first of all, it can give us a pretty simple result of an integral. Suppose you have some function that is known to be a potential field. For example, let's say this f equals r. Say I want to integrate r along a very complicated curve. Let's say we can make it even 3D. Say this is 1, 1, 1. This is origin. Right. So we have a very, very complicated curve. It's really hard to parameterize, but we can tell the answer because we know this r equals the gradient of that. Right? And this equals x squared plus y squared, or plus z squared if you have a 3. And then it's along this c, but we know it's just the function evaluated at b, which is 1, 1, 1, minus the same function evaluated at 0, 0, 0, and that is 1/2, 1 squared plus 1 squared plus 1 squared minus 10, that's 0, so it's just a 3/2. Okay, so you can see if you have a conservative field or potential field, then the integral along the curve is really simple. You don't need to know what is in between. You only need to know what is the starting point and the ending point. Okay, that makes the integral really simple. Now we can restate this in a theory. If f is a gradient field, then the integration of f along the curve only depends on its starting point and end point, or we can call it path independent. That is, if you have a common starting point and end point, it's called A and B, then it doesn't matter whether you go along this path or that path or some other fancy path, they all give you the same result. Right? Because it only depends on A and B. That's what we say path independent. And it can be written in another form. If you integrate along the closed path, C, and then this must be 0. By closed path, I mean something like that, which you can regard as A equals B. Right? Because you start and end at the same point. So this is a C. Right? So for closed path, A equals B. And in fact, it's vice versa, because if you know for closed path the integral equals 0, then if you have C1 and C2, then you can regard this, which means C2 followed by negative C1 as a closed path. So integral along this closed path is 0, implies the integration along C2 equals the integration along C1. So you can see the last statement implies the previous one, right? Because for any C1 and C2 with a common starting and end point, if you merge them, with one of them inversed, you will get 0. So it implies the integral along C1 and C2 are the same. And this also implies that, because if the integral is path independent, then we can recover this f by choosing any fixed starting point, let's say A, then any other point, let's say call it x, y, z, then you just integrate this f along any curve starting from A to a given point. Okay, any path. Just integrate it along this path, you'll get a result, right? And because this is path independent, so it doesn't matter how you choose the path, you'll get a unique result. And I claim this unique result will give you a function that gives you this gradient field. Because if you take the gradient of that function, then you will see it's by the fundamental theorem of calculus, you can see it's just to recover this f function. Because you take the gradient, then you can see, say, in f direction, then you can move it in x direction a little bit, right? So this will give you the x gradient, that's f. So they're all vice versa. So the three conditions, gradient field, path independent integral, and a vanishing loop integral, they're all equivalent, right? So that's what the fundamental theorem of line integral tells us. Finally, we are ready to prove, well, not completely, at least state the theorem of potential field. F is a potential field if and only if P, okay, X, so Py equals Qx. And here F equals PQ. Sorry. And this is for 2D. For 3D, we have a more complicated condition, but similar. We will mention that a little later. So here it means the derivative of p over y, and this is the derivative of q over x. All right, let me prove it. Well, if this theorem is correct, then you can see if you know the field, meaning you know p and q, then you can just check their derivative, see if they're the same. If they're same everywhere, okay, everywhere. If they're same everywhere, then we can claim it's a potential field. All right, let me prove it. First, if this is true, then p equals fx and q equals fy. Right? You know, by the definition, potential field. And what is py? Py is fxy, and qx equals fy then x. And they must be the same because by the the Clarion theorem, cross derivative does not depend on the order of the derivative. So we showed that one direction, this to that is easy. Right? The other way, if py equals qx, then we don't know there yet, but we will show next class that by something called Green's theorem, the loop integral of pq is always 0. And then, according to what we just discussed earlier, it means there exists f such that pq equals fx fy. So that means it's a potential field. Okay. So the proof is not complete because we don't know how to. We don't even know what is Green's theorem, right? But we will show it next time. Okay. For now, let's say we take it for granted, and we will see how we use it to determine if a field is potential field, and if it is, how do we construct this gradient, not gradient, the potential function. All right, let's give an example. First one, f equals negative y x. Is that a potential field? Well, let's check it. That's p, take its y derivative, so negative 1, and q, take its x derivative, that is x over x, that's 1. And of course, they are not equal, so it's not a potential field. Alright. Now, let's look at something more fun to look. I don't tell you the function, but I plot it. The function is like this. Not function, the field. Alright, so given this plot, do you think this is a potential field? Is f a potential field? I say it's not, because if you integrate along this path, along this path, closed path, or this one, closed path, what do you see? You see f dot dr is positive, because f is parallel to dr at every point along the curve. So if you integrate, it's still going to be positive, and it's not 0. So it's not a potential field. Okay? Because we said that the potential field must have the loop integral to be 0. And this time the loop integral is not 0. So this means it's not a potential field. Right? So you can tell it from a graph without even, a given function. Let's try this one. F equals y e to the x plus sine y e to the x plus x cosine cosine y. Okay, very complicated, right? So, do you think this is a potential field? Well, we wouldn't know it, let's say 2 days ago, but now we know it because we can just check it. Py equals, remember p is supposed to be the partial derivative, the x derivative of function, so we take the y derivative, right? So py and qx. Take the y derivative, so y equals a variable and x is a constant. Okay, and what is qx? Now x is a variable and y is a constant. Yes, they are the same, right? They're equal. So it's a potential field. Well, let's find out the f so that this equals the given function. Right, let's see what is the given function. Y e to the x plus sine y and e to the x plus x cosine y. Right? So, and I said earlier, we can just, let's say we choose the origin and choose here to be f to be 0. Then for any other point, we can just choose an arbitrary path to integrate this f along this to get an f there. But we don't have to be so random. We can just do it first along x, then along y, right? So let's find it. F x y. You can just integrate along this curve, a straight line, and since along this straight line, you can just do p dx. Then along this vertical line, which is q dy, right? So what is p? Y e to the x plus sine y, right? And plus q dy we'll figure out later. Then this will give you, when integrate along this direction, x is changing and y is a constant, right? So we can fix y. And sine y and times x. X is a variable. Okay, then we need to integrate along the other direction. This time x is a constant and y is changing. So you have to plug in the value here. Here it's a x 0. 0 and from 0 0 to x 0. Right, then you integrate the other one. Plug in q, so you get integrate over that. You get e to the x times y plus x sine y, and you plug in the two limits from x0 to xy. Right? So x0 will give you, when y equals 0, this happens to be gone, right? So you get nothing, right? That's nice. So we only have the second term. So e to the x y plus x sine y Well, actually notice this and that are the same, right? So we we can just cancel this directly. So just that's the answer. Okay. And this procedure can be simplified a little bit further. Suppose you are given P and Q and you have verified the existence of F. Then you can just solve it in an equation. So instead of constructing this, this first horizontal and then vertical path, we can just solve this F. We can just do this. What is F? F must be the integration of P along X. And the integration will give you a function, but since now y is a constant, so y is fixed for the moment, so the result is not just a plus c. Usually indefinitely will give you plus c, right? Now it gives you something called f, an arbitrary function of y, because this function of y, when you take x derivative, it will be gone. So you'd always recover p when you take x derivative. Right? Then how do you determine this h of y? You can just take its y derivative. So take it fy. It must be something plus h prime of y, and that must be equal to q. And matching them, you will see what is the h prime, and you can integrate that to get h. All right, let's see another example so you can see what I'm talking about. Let's say f equals 3 plus 2xy and x squared minus 3y squared. Okay, is that conservative field? Let's check it. Py equals, take it y derivative, 2x, and qx equals x derivative, 2x, they're the same. Right, so f is conservative. Alright, let's find out f. So, according to the definition, fx must be p, and fy must be q. Alright, let's see. How do we find out f? F equals the integral of p over x. Then you will get 3x plus x squared y. Well, if you just leave it like that, it's not going to work. Because if you take its y derivative, to get that, what do you see? You have this is gone, and that will give you x squared. So it's x squared, not x squared minus 3y squared. So what do? You add an arbitrary function y. How can we do that? Because whatever h is, when you take its x derivative, you will still get the same thing. So let's take its y derivative. So you get x squared plus h prime of y, and that must be equal to this. You can see the h squared cancels, so h prime y equals negative 3y squared. And what is h? H equals negative y cubed. Well, you can add a plus c there, but it's not necessary because we only need to find out one of them. So that means we can write down f now. Remember that? 3x plus x squared y. Now you just add your h, which is negative y cubed. Alright, so that's your f. You can see you can recover this f by just solving these two equations. These two equations. Instead of just integrate along some curve. That's equivalent, but this way is easier. Okay. Now let me briefly mention what happens in the 3D case. If f equals p, q, r, then how do we know if it's conservative? Well, it's very similar, but it's just a harder to prove. So if f equals the gradient of a potential, then it's fx, fy, fz, right? Then you can see that they are the same. So we'll have some terms that are the same. Py must be fxy, which is same as fyx, which is qx, as we know earlier. But now you can also get these two. So you get qz equals fyz equals fzy, which is ry. And you can also get p and r. It's rx equals fzx equals fxz equals pz. Right, so you get a 3 equality. First one between pq, second one between qr, third one between rp. So you have 3 equality between the 3 components, pqr. And the converse is also true. If all of the 3 equality hold, qz equals py and rx equals pz, then the field is a gradient field. Okay, the proof is similar. It's based on something called Stokes theorem. It's a 3D version of Green theorem. Okay, but it's harder to prove, and we won't really prove it. We're briefly mentioned in the end, but the conclusion is pretty similar. Just doing some comparison, we can guarantee the existence of this potential field. Okay, let's see an example. Suppose you're given a field x, y, z equals y, z, x, z, x, y plus 2z. I want to integrate this field along a path that is defined to be this way. C equals cosine t, 2 sine t, and t, and t goes from, t goes from 0 to pi. Alright, so find this integral. Well, if you remember, we have to write down this f in terms of y, z, x, etc. Then in terms of t, and this dr will become x prime, y prime, z prime, everything in terms of t. So it's a very, very long formula, right? And then we integrate. However, we can do it easier. We can do it in an easier way, because if you notice, this f is a potential field. Then this word just becomes f the end minus f the beginning, right? F and minus f start, right? So let's check if it's the case. Okay, if it's the case, then it's much easier. Alright, let's see. What is our... Okay, remember this is supposed to be x derivative. This is supposed to be y derivative. This is supposed to be z derivative. So let's check their cross derivative, and cross derivative here. So let's see. Py and qx. Take the y derivative, you get z, and x derivative, here z. Good. Then next one, Okay, let's do it here. So QZ and RY, right? QZ equals X, RY is also X. Good. Again, check. The last one, we do it here. PZ and RX, right? PZ and RX. What is PZ? Y. And what is Rx? Also Y. So they're all correct. So it's a potential field. Okay, so let's try to recover this F. Well, it's not so easy, but look at these three terms. It's kind of easy to guess. So what is F? Well, you can guess that. Because when you take x derivative, you get yz, y derivative, you get xz, z derivative, you get xy, right? But you have an extra term that is not here, but that's easy to fix. Just add that. Then when you take xy derivative, you get nothing but z derivative, you get 2z. So we have recovered this f, right? And once you figure out this f, the integral is really easy. So it's just f, you plug in the endpoint, you plug in t equals pi, so that's -1, 0, pi. -1, 0, pi. Minus the starting point, 1, 0, 0. Right, and then that's just good. The product, all of them is 0, so this pi square minus 0 is just pi square. Done. Alright, so you can see if you can identify a potential field as an a field as a vector field as a potential field, then the integral is really simple. Alright, that's it for 16.3. See you next time.